Welcome to today's webinar, Devil in the Details, How to Achieve Accurate Fatigue Calculations with Coreform Cubit and Endurica CL. I'm Matt Cederberg, a co-founder and chief strategy officer at Coreform. And today's webinar will be presented by Dr. Will Mars, founder and president of Endurica, Mark Bauman, a project engineer at Endurica, and Greg Vernon, director of product and expert Coreform Cubit user at Coreform. Just some housekeeping for today's webinar. This is being recorded. Please ask questions in the chat through the Q&A throughout the webinar. We'll either type back answers during the webinar or we will have a little bit of time for QA at the end. Today, we will introduce first Coreform and then Endurica, and then dive into the details of how to use these two pieces of software together to achieve accurate fatigue calculations. So first, to introduce Coreform, Coreform develops next-generation best-in-class technology to improve your simulation processes. So if you have existing solvers and you want to create better meshes for those solvers, we have Coreform Cubit, which is best-in-class meshing software. If you want to accelerate your entire simulation workflow, and you're even open to introducing a new solver, we've developed Coreform Flex, which radically accelerates the entire simulation workflow with very fast, fully automated preparation of mesh and geometry for simulation. So if across that entire spectrum, no matter where you're at, if you want to accelerate your simulation process, then we are interested in talking with you. To introduce Coreform Cubit is a little bit more because that's the focus of today's webinar. Coreform Cubit is been developed for the last several decades. It is used across many industries, including defense, aerospace, automotive, and tire. Some of its key features are being able to import CAD from a variety of native and open source CAD formats, ability to clean up that CAD geometry, have best-in-class semi-automated hex meshing, a lot of control over mesh properties and quality, whether it's hex or tet meshes. A lot of people use Coreform Cubit because of its advanced Python and scripting capabilities. And also, Coreform Cubit offers very flexible licensing that can give you a cost-effective solution across your entire global team to use Coreform Cubit for your meshing solutions. With that, I'll turn the time over to Will to introduce more of the Endurica software.
Thanks, Matt. It's great to be here. And let me start by just saying a few words about Endurica. Our tagline is Get Durability Right. We are focused very much on elastomers. So it's Get Durability Right for elastomers. And we also have a big focus on simulation. This is, we've got a whole toolbox of tools for the different workflows that you might use for doing fatigue life prediction in elastomers. This is year number 17 for us. I founded the company in 2008. Our tools are used at more than half of the largest rubber companies in the world. Kind of our mantra is accurate, complete, and scalable. As far as the tools that we're bringing to bear. Today, we're going to really use a simple workflow for this demo, but the tools are quite complete and can do a great job doing life prediction for elastomers. We offer softwares our crown jewels, but we also can help people get the testing equipment for their labs to measure the parameters that go into simulating durability for a rubber part. We also obviously do simulation services if people want to engage us for consulting types of projects. And we do training. We teach people how to use these tools and how to get durability right for elastomer problems. All right. So the title of our webinar today is Devil in the Details. And what I mean by this is that if you look at, rubber invariably is a molded part. And molds generally have a all sorts of interesting features on them. Right, we use molds because we want to make interesting shapes. Um, and there's a lot of times we're going to have lettering that we want to mold onto the part. Molds will always have some kind of injection port or vent on the part. In many rubber parts, there are, let's say, voids or cutouts that have, tight radii that, and all of these features that I'm showing here for these various applications. This is a bushing. This is an automotive bushing for a car suspension. This is a motor mount, hydro mount. We've got a tire here. We've got an exhaust mount. We've got an air spring. Um, and in any of these applications, these small features that often as modelers we might want to airbrush away and just ignore those small features. But the trouble is that sometimes cracks start at those places because all of those features can serve as stress concentrations. And so when you're modeling durability, you want to make sure that you've captured any features where you might have a crack. And of course, this raises all sorts of interesting questions about how do you make sure you've got the right amount of mesh refinement. And that's really what we want to unpack here today and show you how these tools work together to get you what you need to deal with these issues. We're going to focus today specifically on the example of an automotive bushing. And we picked this one because it's got examples of all sorts of interesting things. First of all, we've got in the cutout here, you can see there's a tight radius both in the sort of around the cutout direction, and then there's also a radius on the edge of the cutout. So there's some fairly tricky geometry there that we want to get right. Um, and so there's that. We also have a bonded edge with a little bit of a radius at that bonded edge that you can see there. And then finally, we've also got this injection port where that's where the rubber squirts in while it's still in its liquid phase before it's vulcanized. And then after they pop it out of the mold, there's usually these little nubs on the part. Um, and sometimes they trim them off, sometimes they leave them. But here we've gone ahead and included that. And obviously the importance of these nubs can vary. If you put this little port in the wrong place, it can be a stress concentrator. It can be a place where cracks start. Hopefully, when you design your mold, you put this in a place where it's not going to do anything to the part. But that's why we do the analysis, right? Is to figure out where we ought to put these things. As we do the analysis, I just want to, we're not going to spend a lot of time talking about how we characterize the material, but just as an example, this is the set of material properties that we've assumed in all the analyses that we're going to show you today. We're using an Ogden hyperelastic model to describe stress strain response. We're using the Lake Lindley fatigue crack growth rate model to describe the crack growth behavior. We've got a strain crystallization model. And we've calibrated the crack precursor size, which in this case was about 21 microns. Right, the Endurica code assumes that every location in the part contains a small crack precursor. If you get out a microscope, you can see it as a undispersed carbon black. But when we calibrated that, we came up with a size of about 21 microns. This bottom plot is what we call the Hay diagram. It's just a map showing how fatigue life depends on mean strain and strain amplitude. And this diagram is computed from the material property set that I've shown above here. This is a material that we used in a paper that we published a few years ago at SAE. And here's kind of the base model. The boundary conditions on this, we're going to fix the outer boundary of the metal can on the bushing. And then on the inside, we're going to apply a radial load. So there's a control node here, and we're just going to push on that, push that to the right here for an 8 mm radial displacement of this inner metal relative to the outer can. The rubber is bonded perfectly to both the inner metal and the outer metal. And I also want to point out that this metal can, if in blue here, you can see that that right now there's no contact between that outside can and the bushing, but as we load this, we're going to see the rubber is going to kind of squish out, and there's going to be an opportunity for contact between the injection port and the outer metal can that we're going to be interested in. So there is a contact model there. All right. Here's kind of a look at just for one of the meshes. We'll talk more about the mesh here in a minute, but just to show you kind of the kinds of deformations and motions that we're looking at. So first of all, in the top row, you're looking at a section view. We have the undeformed geometry on the left, and then as we apply the load, you can sort of see that one side of the bushing squishes out or in compression, the other side's in tension, and then I've highlighted here. We're going to look at some specific areas. We're going to look at the corner singularity. We're going to look at the high curvature area on the cutout. We're also going to look at this injection port and look at how these potential failure modes do under fatigue loading. All right, and you can see for the injection port, as the rubber squishes down, you see it coming into contact with the outer metal can.
Yeah, so as Will mentioned, we're going to take a look at a couple different approaches and compare different approaches with mesh generation. One of the approaches we're going to look at is tetrahedral mesh generation. And the nice thing with mesh generation from a user standpoint is that it's largely very simple to produce. Very minimal input parameters are needed. You pretty much let the computer build your mesh, do a quick review, maybe clean up a few spots, maybe defeature a few spots, but it's pretty automatic, and you let the solver then crunch on the solution. As we're going to show, though, that oftentimes can lead to overly computationally intensive problems, and maybe is not quite as automatic than as it might at first seem. So we're also going to show hexahedral meshing, and we'll compare the results between hex and tet meshing. And so as an overview for hex meshing this component, what I essentially did is break down, there's this really complex bushing. We don't want to defeature these potentially vital regions like these fillets, and so we're going to handle them. But there is an overall symmetry to this problem. So we're going to break it down to the simplest kind of region and then reconstruct the full 3D volume. And what I want to show, at least today, is a few tips and tricks that I used when I was meshing this component that can help you with meshing bushings, but can also be relevant to other problems. So the first of these is to recognize when you're first looking at your problem to see, do I have any symmetry that I can take advantage of? And there's obviously symmetry for a simulation, but in this case, we're going to have this non-symmetric loading. So we want to make sure that we're considering, we can still consider the symmetry from a meshing standpoint. So we'll mesh one octant of this bushing, and then we will just reflect it to recover the full three-dimensional volume. And so there is a tool in Cubit for copying geometry with copying the mesh as well. So that is tip number one, is to take advantage of symmetry. The second tip is, in general, when you're doing hex meshing, that you should try to focus first on challenging regions. Specifically, we've said, hey, these fillets are the regions that I'm concerned about. So I want to make sure I get a quality mesh on these fillet regions first. And in particular, when you have fillets along a complex spline like we have here, that's really going to be the most challenging kind of region. So not only do we want to first try to focus on our regions of concern and our challenging regions, but if you have a region that's both critical and challenging, you should really do it first. So that's what we did here. The second part is, or the third tip is to consider smoothing. So especially in this case where we have this complex spline that we're then trying to sweep a hex mesh across, splines are really challenging. They oftentimes have different, they're parameterized separately from each other. And so initial meshes, as you can see here in the before image, oftentimes will actually be invalid. You can see the scale Jacobian here is negative, telling us that those red elements are actually inverted. And so what we can do is we can apply smoothing. In this case, I used a Jacobian, Laplacian smoothing after the initial mesh, which then recovered a valid and pretty high quality hex mesh in this case. So just because your initial mesh comes out poor, always consider smoothing in Coreform Cubit. The fourth tip, which really kind of helped accelerate and let me iterate on trying to build this mesh, is to use journaling and scripting in Cubit. This is really kind of the secret behind effective meshing in Cubit. What I tend to do when I work is I'll have both Coreform Cubit GUI up, which you can see on kind of like the left figure, and I'll have it on half my screen, and on the other half of my screen, I'll have the journal editor open for Cubit. If you have multiple screens, sometimes I'll put that journal editor on my second screen. And what I'm doing is I'm using the Coreform Cubit GUI, like the command panel, to be able to help guide myself with creating or decomposing my model to make the mesh. And then there is a history tab, which you can kind of make out in this screenshot at the bottom, where all of the commands I've been running through the GUI have been logged. And I copy them. So you can see I've got my selection copied in blue, and then I'll paste them over in my journal file. And what I'll do is that then, as I'm building that journal file, I'll kind of then tweak it around like I'm a programmer to make sure that I've got things structured in the way I want them. Maybe I'll even add some comments to let myself know what I'm doing. And what's nice with that is that gives you the flexibility that, maybe that last operation I did wasn't really what I wanted to do. There is an undo functionality in Cubit, but oftentimes I might want to roll back like 10 or 20 commands. Like maybe this was a dead end. And having a journal file allows me to quickly go back and start over. Or maybe I need additional geometry. And so maybe the operations are the exact same that I want to do, but maybe the IDs have just changed. And so rather than having to click through a whole bunch of commands to recover where I'm at, I can just simply change a few IDs and replay my script. And so that's really a powerful feature of Coreform Cubit. The fifth tip that I have is based on this, which is to incorporate then Python into those scripts. So in this case, I've got some complex fillet and I want to kind of chop off the top kind of region. And I could just click a point and arbitrarily pick a point to cut at. But if I want this to be repeatable for maybe future bushing versions, maybe I've decided, I want to always make sure that I'm cutting maybe at the location of maximum curvature on that curve. And that's something that then I can repeat on every other single bushing that's going to come in. And so Coreform Cubit has this robust Python interface. What's nice is that within a journal file, so I can have Cubit command syntax and Python side by side by using what's called shebang notation. That's a term that comes, if there's any Linux users, that's a term that comes from Linux, where if you do a pound sign, or I guess now it's called a hashtag, and an exclamation point, you can then tell it I want to be Python or Cubit, and I can switch back and forth. So you can see here, I've said, I want to prepare this core region. Let me switch over to Python. For this, I need the math library and the SciPy library, because I'm going to do an optimization. Here near the bottom, you can see I'm using SciPy's optimization routine, minimize scalar, with a Lambda function that's then calling off the various Cubit Python API features to be able to say, get the curvature at a certain position on this curve. And what I have done myself, and when I was in my former life, when all I did was pretty much meshing, I built up a library of these different little Python routines that I found were really helpful for meshing certain parts. And that kind of became my own personal intellectual property that I had as an engineer I share it with my team, but these are things I became comfortable with, and I have my own little library of these little helper routines that then I could reference in future projects. And so that's really a helpful thing to be aware of. The sixth tip is compositing. Other tools you may be familiar with this. It's called virtual topology sometimes. And in fact, in Cubit, in the user manual, we refer to it also as it creates virtual geometry. But one of the challenges that CAD-based meshing tools have is that they respect the CAD. They first mesh, all the vertices, and then all the curves, and then all the surfaces, and then they mesh volumes. And so if you have like these curves, like you can see this arc here that comes really close to this fillet, it's going to try to respect that, and that can over-constrain the mesh that results in poor quality. And so compositing is a way for us to say, composite multiple surfaces together into a single surface and ignore maybe this additional topology. So if you go to the next slide, then we can see now I have used the composite function in the command panel. You may be able to see it as this middle image, a very faint kind of light pink or light salmon line, where that curve is now represented as a dashed line of a lighter color to let you know that it's there, but we're just going to ignore it. And you can see that on the right, that entire curve is ignored. And again, if we want maybe a finer mesh, we can now just provide a finer mesh, but we're not now constrained to that kind of arbitrary CAD curve. And then finally, a third example. So that's like just to get a better mesh quality. But in this case, the fillet was actually unmeshable just because of the way that we had to produce our web cut here resulted in these, you can kind of see like these little triangle regions that would essentially force us to have a single layer of wedge elements and then go to hex elements and then come back on the backside back to a final layer of wedges. And Cubit doesn't really understand how to build those kinds of meshes. So what we do is we say composite those three surfaces into a single surface that now Cubit can just pave all hexes along. And so it's not only necessary or helpful or beneficial for quality meshes, but is oftentimes necessary to even get a hex mesh in the first place. The last tip I want to share with you today is on imprinting and merging. Generally, again, the workflow that you're trying to do is I want to build a contiguous mesh, but I have to cut my geometry into the separate meshable regions. We use the scissors icon to really give you this idea in the image shown here that I am cutting things apart. And so they're now disconnected. And so now if we want a contiguous mesh, we need to pull them back together. And that's what merging does. But imprint sometimes is needed to enable that merge operation to happen. And so if we go to the next slide, we'll show what this kind of how this works. So in this case, maybe I've had a single volume that I then cut into a cylinder and a cube. And as you can see here, they are disconnected. Their meshes are completely different from each other. They are also not mergeable. I can't merge a square with a circle. So this is where we need to do an imprint operation before merge. So what the imprint does is it takes those nearby entities and it projects and enforces that topology on those surfaces. The regions are still disconnected. You can hopefully make out those meshes still do not align. So the merge operation then enforces that continuity. And as a last, just zoom in of what's really happening here at each stage. So I've kind of pulled these surfaces apart so you can see this. Again, I've got a square and a circle, which are going to have their own separate meshes. I can imprint, but I still have a kind of a square with a hole cut out with a circle and a separate circle. And the yellow and the green are still disconnected from each other, and they can still permit, or they still will have their own meshes. That merge operation gets rid of that duplication. And now you can see I've really only have two surfaces. So I mesh the circle, and that is now shared on its boundary by both the cylinder volume and then that cube volume that we have. So those are those operations that happened. And so really getting good at understanding how the imprinting and merging happen, and even how those interplay with doing compositing is really a key thing to understand with Coreform Cubit. So that's all I have for sharing the tips and tricks for meshing with Cubit. We will be producing a video and showing the process of actually meshing this entire bushing. We'll put that onto YouTube shortly after this webinar itself goes live, and we'll share our scripts and stuff.
Yeah, great. So this is Mark here from Endurica. I went ahead and ran the fatigue analysis with our Endurica software on the bushing. And so this is our first slide just talking about the workflow steps of how we run an Endurica fatigue analysis. The first part on the left, you'll see we start with material properties. And we have all sorts of different modules with Endurica. It starts with the basics. There's a hyperelastic and a core module. The hyperelastic getting your stress strain curves, and core getting your basic fatigue models. And then depending on your application and budget, what's important to your project that you're working on, you might choose to include, say, softening or strain crystallization. There's an aging module. There's a self-heating, just to name a few of them. But there's really a full suite of materials that you can pick from. And once you've got those material properties, those will feed your finite element analysis and also feed your Endurica CL analysis. So with our FEA, we've used Abacus for the webinar, but our Endurica software works with other fatigue solvers as well. And once you've got your finite element analysis set up with the mesh, and we'll look at several different meshes here, all of the loadings and boundary conditions. Once you've solved your FEA, you export the strain history to our Endurica CL software. And our software uses a couple of different technologies here to get you an accurate result. A couple of them are the critical plane analysis and rain flow counting to parse through the history. And using the material properties and the strain and those critical plane and rain flow, we have a fatigue life prediction from our Endurica software. And you can view that right on your FEA model. So this is our first slide of the bushing, the fatigue results. As you can see, we've got 7 different meshes here. We had tried to run 2 more in the bottom right corner, but that was kind of over the limit of our computer specs. This was using a 128 gigabytes on the RAM, and it was out of memory for the 2 with the red boxes there. But starting at the top, the hex meshes with linear elements, you can see just in general in all these steps, the hex meshes will give you quite a bit cleaner results. There's kind of a smoother color band, and the results kind of agree a bit better. As we move into the middle row, that's the TET mesh with the linear order. The linear TETs can give you lots of accuracy problems. If you kind of read the documentation for FEA solvers, they point out all sorts of ways that linear TETs can be inaccurate. So we want to be careful about using those results. And as you can see, the colors kind of spread more on there. The first section view slide, I wanted to show you these. You can see the overall, you might look at the kind of center interior of the bushing, and that kind of looks like the critical area. But as we see on the next slide, there's a couple of other critical details that we might have left off, that the outside corner here and the port and the cutout as well. So if we zoom into these other important areas, this is the outside corner. This becomes a singularity as the outer surface is bonded to the metal, and then the top surface is allowed to stretch away from it as it's loaded. And so we've got on the top, the hex meshes produce the nice clean results. And as we refine the mesh towards the right images, you see the life just keeps on dropping as we refine the mesh, getting smaller and smaller elements towards that singularity tends to keep dropping the results. And I'll point out here that we have checkerboarding in the coloring when we look at the TET meshes, especially that quadratic TET mesh at the bottom. The checkerboarding is a sign that it may not be accurate. So you want to be very careful about using these TET meshes here. that checkerboarding is definitely a sign to be careful with it. And the results just look kind of ugly too. I wouldn't want to give this to a customer with the coloring the way it is here on some of these TET meshes.
I just want to break in and make one comment on the, if you look at these different features, the cutout, the bonded edge, and the injection port. The bonded edge is a bit of a special case because the bonded edge, because it has sort of this stress singularity. As Mark is showing on this slide, no matter how much you refine the mesh, the life just keeps, the stress goes up and the strain goes down as you look at smaller and smaller element volumes. So when you have this type of situation, refining the mesh may not get you out of jail, let's say. And so that's a case where you might want to take a slightly different approach, and maybe consider how a small crack in the model would behave. And for corners in these kinds of applications, it's sometimes the case that we normally expect, and in most places in a part, the bigger the crack gets, the bigger the tearing energy driving crack growth. But in particular at this type of bond edge, it can happen that increasing the size of the crack at the bond edge can actually result in lower tearing energy on the crack. Particularly in this case, if the crack is in tension, right? So if you're shearing it and you have that singularity, there's on one side of the bushing there's going to be tension at that bonded edge, but if you look at how this is a plot from a paper by Gent and co-authors where they plotted the tearing energy on the crack as a function of the size of the crack, and you can see on the side of the bushing that has shearing causes tension at that bond edge, you can see that as the crack grows, there's a bit of I guess it increases for a little bit, but once the crack becomes more than a fraction of a millimeter, that tearing energy is decreasing to a point. So there's a good chance that crack is actually going to arrest. And now on the other hand, if that bond edge is loaded in compression, then it's going to keep going up like we might normally expect. So again, just a recommendation that if you're looking at specifically at a bonded edge with a singularity, you're going to want to look at how the tearing energy scales with crack size a little bit more carefully.
So the next critical area we're looking at here is the cutout, and there's a small radius here. The top row, the hex meshes, you can see that we're increasing the life as we refine the mesh. So when you look at this tight radius, if you have coarse elements, it's not kind of accurately discretizing that radius, and so there's larger angles on the coarse mesh between the elements. And when you refine the mesh, you'd get a better result here as the element angles between them gets more accurate as you refine the mesh. And on the TET meshes, you can again kind of see the values jumping around a bit more. It's just not quite as nice looking, especially with the linear TETs. You got to be careful with the accuracy on that. And the quadratic TET at the bottom, you can see that one as well. This is the injection port. And on the right underneath the fatigue life legend, I've kind of highlighted the deformed position of it. The red arrow is pointing to the injection port. It gets basically completely smashed until it's flush with the surface around it. So it kind of has a compression and a shear loading on it. And as we can see, the critical life areas on the interior, kind of right at the middle of it. This is a section view through the injection port. And so the hex meshes, again, it gives you a cleaner appearance and a little bit more confidence in the results. The TEP meshes, especially looking at the inside of this, the coloring is kind of all over the place with the element values. It jumps around, not a very clean result to display. When you get to the quadratic TETs, it's a little bit better on the accuracy. The quadratic TETs are quite expensive to run, so as on the other slides, it wasn't able to run finer meshes with the quadratic order. And this is just a summary of all of the different areas and meshes that we ran. The degree of freedoms is the number of equations in the model, and that kind of correlates with the runtime in the next column. And so as we increase our refinement of the mesh, the runtime is obviously longer. Our quadratic, again, that wasn't able to solve, and our convergence is also dependent upon our mesh refinement. As you get smaller elements, it can become harder to converge the model.
All right. Thank you, Mark. So, if we kind of take the the set of results that we saw in this study and across other studies that we've run as well, you can kind of boil all this down into a little checklist that maybe you want to follow when you're doing a fatigue analysis on a rubber part. First of all, with regards to places on the part where you've got a large, large curvature or small radii features, when you're doing the meshing, you want to make sure that those smallest radii are adequately resolved. So, that's a matter of using the tips and tricks that Greg showed, to make sure that you've got enough discretization to accurately capture those results. I thought it was interesting in the study we did here that as you refine the mesh, the life in the region of the cutout, refining the mesh increased the life, and we think that was because at low discretization, there was a large sort of faceting going on, which tended to increase the facet itself served as a stress concentrator, which reduced the life. And then when we smoothed that out and followed the geometry a bit better, we were able to get to a more converged result. So the first thing is focus on areas of high curvature. Those are going to be stress concentrators. Make sure you get those modeled, with enough smoothness. The next thing to look at is when you're evaluating. We don't always have the luxury of doing convergence studies. A lot of times you're have a deadline, and so sometimes you have to operate without a full set of convergence checks. But one thing you can look at is the gradient in the results, and if you see that, like in the example of the linear tets or even the quad tets, those elements lead to a lot of highly discontinuous results between elements. And you have an element with very long life right next to an element with very short life, and that's not desirable. What you want to see is you want to see a solution that from one element to the next is kind of following some kind of sensible trend, right? Has a reasonable gradient, and with the hex elements, we tend to see that quite a bit more. So that's the next thing you can look at. We talked a little bit about corners where you might have a singularity, and it's important to remember, so there's a rabbit hole there that if you don't know better, you can get stuck in. In that particular case, refining your mesh forever and ever is not going to get you out of jail. So what do you do in that case? Well, that's where it might be appropriate to actually model a crack at that location in the part to check how does the tearing energy scale as it grows bigger. You want to take a note of whether you're in tension or shear or compression, and so those are things you're going to want to do. Another, if you don't want to go to the trouble of modeling a crack, another thing that you might do might be to pick a controlled location that's some fixed distance, a small distance away from that edge, and then use that as your benchmark for making A to B comparisons of life. But so that's the guidance for when you have a corner with a sharp edge, a sharp bonded edge. The final thing I'll mention is a topic that we didn't really talk about, and I think in future we'll probably follow this up with more information about this. But one of the practices that we use here at Endurica very frequently is to skin our solid element models with a set of membrane elements. And the reason we do that is the membrane elements do a great job of capturing the plane stress condition. Cracks, if you look at where cracks initiate, it's more common for cracks to initiate on free surfaces than it is for them to initiate on the interior of a part. And so when we pave with membranes, we're ensuring that we accurately represent the plane stress condition that's on the surface of the part. Cubit does have a tool set for setting up these membrane meshes, but we didn't in this work. We didn't look at that, and like I say, we'll probably follow up with more information there. But that would be another recommendation in helping to get converged results for your fatigue analyses. So in summary, like I say, you've seen here that some examples of the kinds of features where cracks can start in rubber parts. And so, don't just always defeature everything away. You want to think about how much something might be a stress concentrator, and you want to make sure that you properly mesh those. We saw here that linear tets are just not if you've got any other choice, they're just not the way to go. Too noisy. Quad tets can work, but they can be computationally expensive. Linear hexes really kind of come out as the best compromise here. Give you good accuracy, efficient compute time. They do take a little bit of effort, but with the right tools like Coreform Cubit, you can you get your mesh right and get good results. Another thing that's really important, if you if you do want to do mesh convergence studies, it really becomes important to automate the mesh build process, and that's where the journaling and scripting features allow you to quickly iterate. I always like to start with a very coarse mesh, because that allows you to very quickly iterate and solve a lot of the issues that you've got to solve to get your model working. And then once I've got a model where the contact is working and the material model is working and the boundary conditions are working, then I amp up the mesh. And this journaling scripting feature is really handy for doing that sort of thing. So if you're interested in more information on the software packages that we've shown today, you can go to our website or to Coreform's website. Also, just like to briefly mention that if you're interested in elastomer fatigue in the rail sector, one of our users is going to be given a live webinar on April 23rd. So I'll just make a mention. So you can find that on our website and sign up if you're interested.
Thank you, Will. And thanks, Mark and Greg, as well, for the excellent presentations. We have a couple of questions coming in. So first, some molded parts have such complex geometry, such as tread patterns or tire sidewall lettering. So it's hard to imagine including all of the small features. What strategies are available to address such cases?
Yeah. So, the the final element codes do have procedures for, in tires, we like to use steady state rolling. But when you're talking about modeling the tread, that's kind of a lead in maybe to the Coreform Flex topic, where they're using a technology called IGA, isogeometric analysis. And probably Matt or Greg would be the right guy to talk about that one. Yeah.
Yeah, and a couple things would be that we didn't show it today because we wanted to keep some of these features in because they weren't too difficult to mesh. But defeaturing is also a for these really complex geometries can get you a result. There's the old saying that all simulations are wrong, but some are useful. But if there's a simulation you couldn't run because you couldn't get a mesh, well, then it's kind of useless. So, as engineers, we oftentimes have to make these modeling assumptions and defeaturing to be able to get a mesh that we can get a computation on, and then use good engineering judgment to understand or to interpret the results. And so that's another approach that you can take to handle like this case of the complex geometries. And then like what Will was saying, as we mature our Coreform Flex IGA solver, defeaturing will be a thing of the past, and be able to get meshes automatically on these complex geometries. But we'll probably leave that for a future webinar.
Great. Thank you. Question from Dylan. Can you use the type of elements which have mid-side element nodes shifted toward the singularity to the quarter points?
If you want to go ahead, Will.
Well, I can speak to that maybe from the angle of modeling a crack. So in the case where you're trying to model the crack at the bond edge, that might be an approach that you would use. So the answer is yeah, that might be something to try. From the standpoint of actually building the mesh for that, I'll let Greg speak to that.
Yeah, Cubit does support quadratic elements, and so that would have those mid-side nodes, and it supports both the hex 20 and hex 27 types of quadratic elements, and you do have some capability to shift the nodes beyond just what the standard projection to their to the CAD geometry boundaries are. That part is probably better left to a power user who's going to be using the Python interface. And then I'm assuming that the quarter points, is that referring to the quadrature points? I'm not otherwise sure what quarter points is referring to. But I do know that there are some formulations in Abacus, and I would assume other codes that use quadrature with or elements with quadrature points on the surfaces. So I assume something like a Chebyshev type of quadrature scheme. But I don't have a lot of experience using those in these kinds of applications. But that could be a good question for us to discuss maybe on our forum.
Thank you. A question from Bing Yang, referring back to the previous discussion about the new Coreform Flex approach. What's the difference between that and other approaches such as SimSolid?
Yeah, I think we don't really ourselves know enough about SimSolid and those other approaches to really be able to make any kind of comment on them. What I'll say with all of these approaches and with any simulation tool, again, it goes back to like all models are wrong, but some are useful. And I think that all of these tools can really be extremely useful in the hands of engineers who understand how these tools work. And I mean, I can't speak highly enough of of all these different tools that are coming out, either before I was born or the tools are coming out currently. And so what I would say is that read through manuals and read through what's available, use the tools, and see how effective they can be in solving your problems. And at the end of the day, what matters is, can you as an engineer solve the problems that you have in front of you and give good engineering answers to your customers to be able to make critical decisions. And it doesn't really matter what the tool is, as long as it can get you those results.
Yeah, thanks, Greg. I guess just a point of emphasis of where we're going with Coreform Flex, though, is our target is to be able to solve hard nonlinear problems, but with a streamlined model preparation workflow. And so that's really, I know some new tools are targeting designers or non-simulation experts. The intent of Coreform Flex is to provide all of that ease of use that you might have getting a simulation tool accessible to designers, but with the richness and robustness that an analyst would require. Okay, the question from Dalen. I can see from the hyperelastic stress strain curve that the strain can be pretty high for rubber. What kind of strain measure did you use?
Yeah, so the Endurica solver supports a couple different strain measures. And I believe we would have used nominal strain in this case. But the solver supports nominal strain. We support log strain. We support green Lagrange, but I'm pretty sure we use nominal strain in this case. Old habit.
Yeah, thank you. Another question: how do you know whether to analyze a small feature or to airbrush it out?
Yeah, that's a great question. You can sort of imagine that there's, well, in the limit, I guess, in the limit, the crack precursors that exist in the rubber from time zero, you could call those small features, and that's what we're using the Endurica code to analyze. So I would say somewhere, obviously we're using Endurica to look at those small features and when they'll grow. So you don't need to explicitly include those as part of your model. And those have dimensions that are maybe on the upper end, like 100 microns. So I guess so that's a tenth of a millimeter, right? 100 microns is a tenth of a millimeter. So just broadly speaking, maybe rule of thumb, some multiple of that. So maybe a third of a millimeter or half a millimeter is where you might start thinking about if that's going to be something that you want to model at a in a macro model, let's say. But things smaller than that, we tend to treat them as the way Endurica works is these crack precursors. We assume that they're a small penny-shaped crack. And Mark mentioned this idea of critical plane analysis. What critical plane analysis means is that we take that penny-shaped crack and we assume or we calculate what the fatigue life would be, assuming that it takes different orientation. So we try and find the orientation for the penny-shaped crack that minimizes the life. And so Endurica always says that a crack precursor is this small penny-shaped thing. But if you're getting more than half a millimeter, then you should really be looking at including that.
Thanks, Will. Okay, looks like maybe the last question. What solvers is Coreform Cubit compatible with? Greg, if you want to take that one.
Yeah, there's quite a few. I don't have the list pulled up in front of me. We do have it on our FAQ, but I can at least broadly speak to Cubit is based upon the Exodus mesh format natively. So any solver that supports Exodus that generally includes a lot of the government codes, but as well as some open source solvers such as Moose. That's what it's based upon. And then essentially Coreform Cubit can export to then other formats or translate on export to other formats that include Abacus, ANSYS, I believe Nastran is one of them as well. But maybe in the follow-up email that we'll send out to everyone, we'll provide a link to our FAQ that then lists out the full list of formats that we support.